Welcome. This is Sound Science of your Sound of Science portion. We will be simply setting up the problem that I was given to by kenniwithani. A problem being I am looking for the force exerted onto the flag, denoted by this little pictogram, from our beautiful little color guard kindling. So specifically the force that kindling exerts on the flag for the flag to do a proper horizontal. That's going to be where you start off just with the flag in hand at one orientation. You're going to lift the flag. This is overly simplified and not drawn to scale. Release the flag and twist it so when it's up here it'll end up at perfectly 180 degrees once it reaches its highest point. That'll be necessary for me to do my calculations, and once it returns it'll have done a 360 back to the catch right here. That's the basic problem that we have. Is with this setup I need to find the original force needed to actually accelerate this flag upward and twist it so it does a perfect 360 when it returns to our catch position. I'm going to consider this position where kindling is holding the flag before she starts accelerating it upward as my point 1. So any subscript with 1 will denote exactly this point. This point will be my point 2. Any subscript with 2 will be designated to this point. And this will be subscript of 3. That'll just help us out. I'm also going to be considering at some point from here to here there's going to be a projectile time, TP. We'll get to that. From here to here there will be some time of translational time, and there will be a second time which is smaller in between a small window here, which is our time of rotation. We'll get to that later, but I just wanted to point that out for now. And now let's get into the basics of the nitty-gritty details that we actually needed to do to calculate this. First thing I need to know is my basic force that I need for my basic point 1. That's where I have my person just holding the flag steady. So here's our beautiful flag. You can hold it however you wish. Here there's only one force that we need to worry about that's just keeping the flag from falling to the ground, and that's going to be the force of gravity, but more likely the force that counteracts that, which is kindling's normal force. What that means is, right now, the flag is experiencing one force that's trying to pull it down. That's F of G on the Earth. And one force that's keeping it from doing that, that's going to be our Fn. That's basically her hands holding it up. We're going to need that for our final calculation, so basically these two forces are equal, so I can just say Fn is equal to Fg. My Fn is the same thing as the mass of the flag times the gravitational constant. That's just what we're going to call as G. That's going to be our 9.8. So my first force that I'm going to worry about, I'm just going to call it Fn for now. It's going to be equal to mg. We're going to need that later, but that's the first force we're going to have to solve for. But that's only one part of our three-part problem, and this is the easiest one we have to deal with. Next is we're going to have to jump into the force that it takes for her to actually start pushing it upwards. So we'll get into that real quick, because this was just force. What we're going to need is the force required. I'm going to say Ft for translational. Force required to move our flag from position 1, where it's just stationary here, again, not to scale, she doesn't have a neck that large, from our position 1 to position 2, where she's actually had the flag above her and almost at the point of release. The force required simply to do this is going to roll into momentum where she's actually tossing it, but we're just going to calculate it as a straight force that took it to push this object up by that much. I'm going to use this as a quote-unquote impulse problem, and consider that the force from here to here is going to be whatever impulse Kindlin applied to the flag, which is going to be change in momentum. So I is equal to delta P, or in other words, our impulse is equal to our final momentum, which is our mass, times the velocity finally, minus our initial momentum, which is our mass times our velocity initially. Another way to denote what impulse is also your force times time. That's how I'm going to try to find the force here. So I have force times time is equal to mvf minus mv initial, where this is the initial velocity and this is the final velocity. Now I'm going to turn it into terms of this exact problem. That's just the basic equation. This is going to be the force T exerted by Kindlin to the flag times some time. This is going to be time translational, the time it takes from the flag to be at this position to this top position, is going to be equal to mass times velocity final. That's going to be mv. This is considered our point 2, so I'm going to call this v2, minus mv1, because this is our point 1, and this is the velocity at this point. Right before we start pushing the flag up, this velocity is considered 0. So this is 0, so basically this whole term will just get canceled out. So what I have left is ft times my t translational is equal to the mass of the flag times this velocity. Now I just need to solve for my f, which will be fine. So I have f is equal to, ft is equal to my mv2 over t2. Now there's one issue with this. I can measure this mass. I already have that somewhere else. I can measure this time. I get Kindlin to do that. But the problem is I don't have a structure to find this v2. So I don't know what v2 is, so I'm going to have to solve that out through kinematics in my next portion. Then, once I have all my variables here set up, I can just solve for ft. So I'm just missing one bit. So right now I have my force translational is equal to some mass of the flag. We have that measured. We have that measured. v2, this is what we need to calculate, divided by t translational. So I'm going to try to find the velocity to right here. So if I remember my points that I showed you earlier, this is my point 2, where Kindlin has the flag above her just as she releases it. I'm going to consider the point right after. This is point 2. At point 3, Kindlin has released the flag. It is now far above her at its highest point and rotated. It won't matter for this part of the problem, but we'll make sure to keep that for our next part. So right here, if I'm just considering straight kinematics, ignoring that it rotated and just considering it moved up, I can say that we're going to have to cut this bit probably, so I'll restart that because I'm missing where I need it to be. So if we're just considering between this point and this point, what I need now is, I need the velocity here. I need v2 here. I don't know what this v2 is, but I can probably solve for it. I know what this V3 is. This is point 3. So I know what the velocity is when the flag is at its highest point. The velocity here, I'm going to consider it as 0 because once it's at its top highest point when it's in projectile motion, it's going to stop and then start falling down again. So V3 can be considered 0. And now all I would need is some acceleration time if I want to use the equation V final is equal to V initial plus acceleration times some time. So between here and here, this is going to be my V final. So I have some V3 is equal to some V initial, that's going to be V2, plus our acceleration times our time. Since she is no longer touching the flag, at this point there is only one force acting upon the flag itself. That's going to be our Fg, and that's going to be pulling that down, and that acceleration is just going to be g. So I can say that my acceleration is g. Since it's falling down, I can already say that this is a negative g times time. And now I just need the time between this point to this point, which I'm going to have to ask Kindlin to get, and that's going to be our TP for projectile. So I have V3 is equal to V2 minus G, that's just direction, it's okay that it's minus, times TP. This is 0, so I can go ahead and cancel that out. I have 0 is equal to V2 minus G times TP. I'm just going to add this to the other side real quick, plus GTP, and I have that my velocity for the second point should be equal to the gravitational acceleration downward times whatever time it took for the flag to get here to there. That's going to be our projectile time. Now that I've solved for V2, I can take this and plug it back into my force equation. So my force, translationally, just the force to move it up, is going to be equal to mass times our velocity 2 is going to be g times TP divided by our translational time. That's going to be our other force that we have to solve for, including, I'm going to have to add this to our other force that we already found, our Fn, which is just mg. So those two are going to be added together, and we only have one more force that we need to worry about. Because this is a horizontal toss, what that means is it's actually rotating from point 1 to point 3, and then back to point 2. So our original flag is oriented this way. Once it's at the top highest point after we accelerated it up and put a spin on it, it will be oriented at 180 degrees its original, or pi radians. We'll have to deal with that later. But once it is caught, once again, once it's back to its catching position, wherever that is, it will be back to its original 360 degrees. Again, and what we're going to do is we're going to run through the rotational force that she has to apply, or the force that she has to apply to rotate the flag 360 degrees while it's flying around in the air. So I'm going to start off with a projectile part of the rotation. So if I consider my point 2 again, where our Kindlin is simply holding the flag above her, right at the point of release, and then tosses it up into the air, where it is above her and 180 degrees, then this can be considered our point 1 still and our point 2. If I'm considering the rotation of this, the change in its orientation, or its theta, should be equal to the speed of its rotation. We're going to consider that omega naught times whatever time it took from point A to point B, or point 1 to point 2. That's going to be our time. Since this is the initial point of release to highest point, this time is the same time as our TP that we solved for earlier, or that we measured earlier. This delta theta, since this rotated exactly 180 degrees, I'm going to consider this 180 degrees, or better yet, consider that pi, because we're going to work in radians. So the delta theta is equal to pi. We're just going to plug this in. I have pi is equal to omega naught TP. I'm going to need this omega later, so I'm just going to solve for this real quick by dividing by TP. Divide by TP. And I have my omega naught should be equal to my pi divided by projectile time. I'm going to have to take this and send it off to our next portion, which is going to be rotational impulse. And that's a little weird, because we're not going to solve for our force yet. We're going to have to solve for our torque, and then transform that into our last bit of force. So let's do that real quick. If I'm considering a rotational impulse, it's going to be a lot similar to our other impulse, but instead we're going to have inertia times omega naught. This is basically your momentum, except it's rotational momentum, is going to be equal to some torque times our time. This is going to be the time it takes for it to actually place that spin onto the flag. So we're going to call this TR. That's going to be the hardest one to measure, because it's going to be like a very small fraction of a time on the video, but I don't have to do that. That's Kenny's job. So now I'm just going to try to solve for this torque. I found this W naught earlier. As we said, W naught was going to be equal to our delta theta over our TP, or better yet, W naught is equal to pi over TP. So we can plug that in here already. So I is equal to, I times our pi over TP should be equal to our torque times the change in time for our projectile. I'm going to go ahead and solve for torque. My inertia should be multiplied by pi over TP. That's equal to torque. I would divide by this time. Divide that by that time. That's just time P. This isn't TP, this is TR. That's my bad. I need to fix that. This is the rotational time it took. So this is just I times pi over TR divided by TP. So my torque here should be equal to the inertia of the flag. We're going to have to figure out what that is in a second. Times pi over TR divided by TP. Now, I had to simplify this because I don't know how to play with drag and complicated real-world problems, so we're going to just consider Kindlin is tossing this in a vacuum, and the flag portion of her pole is negligible. So this inertia is going to be the same as just a basic rod where it's rotating around the center. The inertia of that is about 1 over 12 times the mass of the rod times the length squared of the rod. So I'll go ahead and plug that in. So my torque should be equal to 1 over 12 mass length squared times our pi over TR divided by TP. Now there's only one issue. I solved for torque instead of force. So I'm going to have to go and change this torque into force based on where Kindle's hands were in relation to where the flag ended up rotating. So her hand is here and here, and she pushes one direction this way and one direction this way to make sure it spins in one direction. Rotationally it'll be spinning this way. Then I can solve out for the force here as F1. I'm going to assume that she applied the same force to both her hands when she was rotating the flag, so this will also be considered F1. So we found our equation to be net force is equal to mg plus mgtp divided by tt plus 2 times 1 over 12 ml squared times pi divided by tp. That's all divided by tr times r1 plus r2. And close that off. Now all we need to do is plug in all of our data. I measured our mass to be 0.83673 kg. Our gravitational field strength, or our acceleration due to gravity, is just going to be 9.8 meters per second squared. Our length of the flag is going to be about 1.8542 meters. And our radius, 1, is going to be 0.23495. R2 is going to be 0.29845 meters. Our times were measured by Kindlen, and our TP is going to be 3.5 seconds. Our TT is going to be 4.5 seconds. And our last time, TR, is going to be about 1.5 seconds. So if I just start plugging this in, I'll get my net force should be equal to 0.83673 kilograms times my 9.8 plus 0.83673 times 9.8 times 3.5, all divided by 4.5. And then we'll have our long complicated bit. I'll add 2 times 1 over 12. My mass is 0.83673 times the length is 1.8542 squared. I need to multiply by pi divided by my time for projectile is going to be 3.5. That's all going to be divided by TR, which is 1.5, times R1 is 0.23495 plus 0.29845. And that, if I just have this plus this whole thing, set that all into a calculator and run it, I should get our net force applied to the flag, which would be about 15.12 newtons. Once again, now that I have my data correct, you can like and subscribe where you please, here, or there. That has been Sound of Science, running through the physics portion of our flag. And I think I'm done here, so I'll see y'all when I see y'all. You can cut whatever you want, Kindle, and play around with this, but I might do my second take later. for now.